Let us begin our fourth lecture. So for today, we want to look at the resultant in 2D. Okay, in this case, we are still looking at particle. To solve resultant problem, or basically to solve problem involving equilibrium, we have to know about free body diagram. What is a free body diagram? Basically, free body diagram is a diagram that we use to represent our actual system or our real world. So normally our real world will look a bit more complicated, but when we want to solve this real world problem, we will idealize it. Our free body diagram is our idealized system. Okay, so in this case, we have a mass that is held by a string. Okay, and this string has an angle of beta with respect to this slanted surface, while this slanted surface has an angle of theta with respect to horizontal axis. And then we have force P pushing this mass, and an angle of alpha with respect to this slanted surface. We have this mass M without any dimension. So that means we can idealize this M, this mass or this block, as a particle. That's why we have one point that represents this mass M. The dimension is not given, or in this case probably not important to solve the problem. Next, we have force P being applied, an angle of alpha with respect to the slanted surface. We remove this surface because we are not interested with the surface, we are interested with the block or the mass M. So when we remove this surface, we will get the effect of the surface towards the mass. In this case, the effect is given by this normal force N. Okay, why we call this normal force? It is normal to the surface. Okay, normal, or basically 90 degrees with respect to the surface. Okay, which surface? Contacting surface. And then we know this mass will has a gravitational pull downward equals to mg. So we have mg always pointing towards negative y axis. And then we have this cable here. Once we remove the cable, we have to add the effect of that cable to the mass, and that effect is being captured by this tension force here, upward and outward from the point. This is what we call as our free body diagram. We free the body from the surrounding, and when we remove other bodies or support, we have to replace these bodies or supports with their effect. In this case, their effect will be counted in terms of forces. The step when we are drawing the free body diagram, we remove other bodies and supports, and we put all the acting forces. Okay, that acting forces can be external. For example, this P is external, out of the system or out of this block M or this particle. And then we have internal forces as well. That internal forces can be in terms of the weight. The weight is always there since we have a mass attached to the block. If we don't have mass, then we don't have weight. And then we need to put all the reaction forces due to any removal made. When we remove our support or our external bodies, we have to replace it with forces. So that's the idea. When we remove this slanted surface, we have to replace it with normal force N. When we remove the cable, we have to replace it with tension coming from this cable. Drawing FBD is very simple. Okay, remove other bodies and support. When you remove other bodies and support, you have to replace the effect of other bodies and support to your particle or rigid body that you are interested in. We will assume in statics especially that our cable is inextensible, or the dimension of the cable will always be the same. And not only that, if you imagine a cable, you fix cable at one side, you can only pull the cable, or basically the cable can only take tension load. If you push the cable will slack. When the cable slack, that means the cable cannot take any load or any force. So in order for any cable to work as any forces within the cable needs to be in tension condition. If the cable is being compressed, then the cable will fail. So we know that for cable, the force must be tension force. Or basically, if we cut any portion of the cable, okay, let's say cut this portion here, I represent this as a point A here, we will have forces outward from this point. This will represent the tension within the cable, always out from any point on that cable. And when it is out from that point, this force is our tension force. Only tension force is out from the point. Normally we have a system of pulley, okay, that is holding cable. Imagine we have, for example, a pulley, right? You can have the same cable passing through the pulley, goes here, and here. Let's say this end is fixed. Somebody is pulling this cable with certain force P. Everything here should be straight. When the cable is passing through a pulley is used to change the direction of cable, and only that. And it will not affect the tension within the cable. Anywhere within the cable, point A, point B, if we cut at these points, for example, we will still have the same tension within the cable. It's just that the direction will be different. In terms of magnitude, it will still be the same. That's what we meant by when cable is passing a pulley, the tension will always be the same, as long as it is the same cable. Once we have two separate cables, then we know the tension within the cable will not be the same. in order for the tension within the cable to be the same, we are assuming the pulley is smooth. There will be no frictional force at the pulley. In the real world, there will be frictional force there. However, for static cases, it is negligible. Lastly, dimensions of pulley are normally neglected, meaning that we assume this pulley to be just a point. Okay, so for example, even though you can have like a large pulley like this, and then you have the cable passing through this pulley, even though the pulley looks like it has certain dimension, if it's not given or negligible, we can assume that it is just a point. So basically, for the free body diagram, we can just draw point A, and then you have two forces, P and another P, due to the tension within the cable acting at point A, and the angle is beta, while here the angle is theta. So we neglect the diameter of the pulley or the dimension of the pulley. Okay, we just assume the pulley is a point. Let's say in this case we have point A, pulley is located at point A, and at the same point we have a mass attached to it. So if we draw the free body diagram of point A, we draw point A, and we know we have two cable that is attached to the pulley. This is basically the same cable, so basically you have the same tension. Okay, so you will have T and another T. And since we are ignoring the dimension of the pulley, so that means instead of having 2T like that, we have only one. Okay, one force vector at the same point A, and the magnitude is equal to 2T since we have two cable, right, pulling point A. And then we have weight, okay, which is given by mg, and weight will always be pointing downward. So this will be your free body diagram for point A. Okay, this is your free body diagram for point A. Now let us take a look at this example again. At point A, if we are interested with point A, so the free body diagram will be, here we have two tension in the cable. Okay, since this is the same cable, so the tension will be the same everywhere. And remember, tension will always be out from a point. So it will always be out from point A. So here we have 2T, and then we have weight equals to mg, pointing downward at point A. Let's say for example sake, we are also interested with point B here, for example. Okay, so how the free body diagram of point B looks like. So we have B. Again, here we have tension coming from the cable outward from point B, and then here we have this direction as the tension at point B. So we have here 2T, and then of course this B is being held here. So we have a reaction force coming from this point here, okay, or this support that is holding our pulley. And lastly here, look at the cable system. We have this T passing through this cable, and it goes to the first pulley, second pulley, and then the third pulley, and ends here. So this is made of the same cable, so the tension within the cable should be the same. And if we are interested with the free body diagram of point A, we'll take point A out and count how many cable is attached to point A. So in this case, even though we see that we have slight angle here, okay, if the angle is not given, we can assume that they are directly vertical. So you can say that we have 3T at the end point A vertically, and then we have weight equals to mg, pointing downward at point A. This is another example. In this case, we are interested with free body diagram of point B. We have point B. Here we are seeing that we have this P is the magnitude of the tension within the cable. So pass through this cable that's going through this first pulley, then passing through the second pulley, and ends here. Okay, so it is made of the same cable. So that means at B we will have P at the angle of theta, and then we have weight is equals to mg, pointing downward, and then at the angle of beta we will have 2P. Why 2P? Because we have two cables here, right? So both of these will pull point P at the angle of beta. Okay, so we have P, P, so that means we have 2P here. Next, we move to this one. Okay, again, we are interested with point B. So we have weight. P is pulling this cable and ends here. So that means we have one cable here, and another cable is being fixed at one end here, and then pass through the same pulley at B, and then ends at pulley at this location here. So that means here we have two separate cable. when we have two separate cable, we will have two separate tension within the cable. Let's say for the first cable here, the tension is given P. The second cable, tension is unknown. Let's say it's equals to T. So at point B, what we'll have T, the angle of theta. And then here we have P. And for the other cable, we'll have T. Okay, so that means we have P plus T here at angle of theta with respect to horizontal axis. What I'm drawing here is your free body diagram for point B. Okay, so free body diagram will depends on location or for point. In this case, we are talking about particle, right? So it depends on point or particle. Later on, when we are talking about rigid body, free body diagram will depends on rigid body. So in this case, we are looking at point B. So just look at point B, remove the external bodies or adjacent bodies, in this case, and the cable and the mesh here. When you remove them, you have the effect of the cables to point B. Alright, we don't look at this point. Let's say this is point A. We don't look at point A. We just concentrate here at point B. So once you have known this, you are ready to solve any resultant to the problem or particle. Okay, so for example, one of the question might be something like this. One thing to note is when we say that the system is in equilibrium, it is in static, right? Or basically, in terms of equation, summation of forces, or basically the resultant is equal to 0. Where basically it should be anywhere or at all points. So in this case, the summation of force is 0 at A, at B, at C, at D, at any point on this system. So that's what we meant by saying that the system is in equilibrium. Why is that? You cannot have a system that is in equilibrium whereby one part is not moving and the other part is moving. That means the system is not in equilibrium. Okay, when we say the system is in equilibrium, all points on the system will not move or will be in static condition. Okay, and in order for it to be not moving, summation of force at any point should be equal to 0, or the resultant at any point should be equal to 0. Normally, we will start off with the point or the location with the most known values. In this case, the question is asking for the tension in cable AB, tension in cable AB, and the angle theta, also for cable AB. Okay, so we don't know the tension, we don't know the angle. So we have multiple points here that we can choose. We can choose to draw a free body diagram at point D, C, B, or A. However, for D, we can do free body diagram for point D, but probably not so useful. Okay, the best point to start is point C, because when we start with point C, we know fluid attached at point C. We also know the angle for the cable CD and also the angle for cable BC. Okay, when we use the free body diagram at point C, we can solve for tension in cable CD and tension in cable BC. Why the tension in cable CD not the same as the tension in cable BC? Because they are made from different cable. Okay, when you have something like this, a knot here, that means you have one cable and two cable. Okay, the cable is not continuous. Unless you have a pulley, the cable will not be continuous. Okay, a knot means you will have two different tension within the cable. Okay, so here we have 1 knot, 2 knot, 3 knot, and 4 knots. Okay, so we will have 1, 2, 3. If we count this as cable as well, we will have 1, 2, 3, 4, 5. 5 cables with 5 different values of tension within the cables. So we'll start off with point C. That means we want to draw the free body diagram of point C. So for point C, take the point with tension CD, and we know the angle is 30 degrees, okay, which is the same as the angle of CD. Next, we have cable BC. When we remove cable BC, we have to replace it with tension in cable BC. The angle of cable BC is 45 degrees, and then we have 25 kilogram mass attached again through another cable, okay, and in this case, we know that through this cable, we will have the same tension, and that tension will be equals to mass times gravity, or basically 25 times 9.81, and the direction will always be pointing downward. CD will have a direction out from point C. Same goes for BC. The direction of DBC will always be out from point C, because we know for cable, the forces within a cable must be in tension, or basically out from a point, in this case out from point C. Okay, once we have this free body diagram for point C, we can start to use this to solve for TCD and TBC. And to solve it, we can again use rectangular component method or trigo approach. In this case, let's say I'm going to use rectangular component method to solve this. We know that for equilibrium, summation of force will be equals to 0. And if we are using rectangular component method, that means summation of force along x equals to 0, summation of force along y equals to 0. So we'll start off with summation of force along x first. Let's say we start off with TBC. We are using x positive to right, y positive output. We will have minus TBC cos 5 degrees plus TCD cos 3 degrees equals to 0. Its weight has no component along x-axis. So this will give us our first equation, which we cannot solve yet because we have two unknowns, TBC, TCD. Next, we have summation of force along y equals to 0. Along y, we will have TBC in 45 degrees plus TCD in 30 degrees minus weight is 25 times 9.1 equals to 0. This will give us our second equation. So we have two equations and two unknowns, TBC and TCD. Theoretically, we can solve this simultaneous equation to get TBC and TD. Let's say I'm taking from equation 1, we get TBC equals to some terms in TCD. Place this into equation number 2. So we have one equation, one unknown, and solve for TCD, values in Newton. So once we have TCD, and substitute TCD to get TBC. Okay, just substitute back into this equation, you have TBC in Newton. Once we have known TBC and TCD, we can move to the next free body diagram. In this case, we will move to free body diagram point B. Okay, why we move to free body diagram of point B? Question actually asks for force within cable AB. So at point B, we'll have TAB at angle of theta, and then here we have weight equals to 10 times 9.1, again pointing downward, and then we'll have TBC, an angle of 45 degrees. Again, we know that for equilibrium, summation of forces should be equal to 0, or basically summation of force along x equals to 0, summation of force along y equals to 0. So we can use rectangular component method again to solve this problem by looking at summation of force along x and y separately. And then we will have our simultaneous equation which we can solve. So that's what we are going to do. Let's take summation of force along x equals to 0. We have minus TAB cos theta plus TBC cos 45 degrees equals to 0. Again, we can rearrange this. Get TAB equals to TBC cos 45 degrees over cos theta. And take this out as our first equation. Next, we use summation of force along y equals to 0. So along y, we'll have TAB sin theta minus the weight, 10 times 9.1, minus BC cos, or if I want to change into sine, that's also possible, equals to 0. So this is our second equation. Then replace the first equation into the second equation. We'll have, so we can substitute for value TBC. Okay, TBC is known, substitute, and then we get theta. Okay, clear? Clear? Any questions so far?
Sir?
Yep.
Can you move to slide 37? We want to find for fx, right?
Okay.
I am a bit confused about TBC cos 45.
Okay. I purposely do that, okay? Because I know this is 45 as well.
Oh, okay. Thank you.
Okay. So cos 45 is equals to sine 45. It doesn't matter.
Okay. Thank you, sir.
Alright. Any other question?
Doctor, I did the calculation and I get the theta for 45. Is that correct?
No idea.
Okay, thank you.
We have to calculate the values actually. Okay, anyone calculate the value of TCD?
I got 45 degree.
For TCD.
On it on 89.83,
400.
doctor.
Yep.
189.83.
TBC.
212.61.
Okay. 12.61.
Yes, doctor.
All right. So anybody else is getting the same figure? Let's say for fun sake, we can also solve the same um, TCD and TBC using other approach. In this case, using Tigo approach, right? So if I want to solve this using Tigo approach, what I need to do, I need to draw it first. Okay. So previously, when we are calculating for resultant, right? When we want to find resultant, we need to ensure that we have three forces in order to use Tigo approach. In this case, it's the same. Okay, we need to ensure that we have three forces. In this case, we also have three forces: TBC, TCD, and weight. Okay, and when we have equilibrium condition, that means that the vector will form a closed loop. Okay, what do I mean by that? Let's say I start with TCD, right? This is my TCD. Okay, and then I will add up with TBC. This is my TBC. My weight should be from the end point of TBC towards the starting point of TCD. Okay, this is my weight. Okay, and if you look at this point C here, okay, we have multiple forces acting at point C, right? Okay, at first we have TCD. TCD will pull C towards this direction, and then you have TBC. Again, TBC will pull point C towards another direction. Okay, towards this direction. Okay, and then you have weight that is pulling it downward. So physically, in order for point C to be in equilibrium or not moving, okay, the sum effect of all these forces will make sure that point C remains at the same position. So that's what happened here. Let's say you are starting at this point. Okay, TCD will move you from this point to this point. And then TBC will move you from this point to this point. Weight will move you from this point towards the starting point. So that means if you are here, the sum of these three forces will make sure that you are not moving. Okay, you are still at the same point. They're applying all these three forces. Okay, so that's what I mean by the vector will be a closed polygon. And if you look at the direction of the arrows, okay, it will make a loop, right? It can be clockwise, counterclockwise, it doesn't matter, but it will be a closed loop. Okay, it's different from resultant problem. For resultant problem, it will not be a closed loop. For example, if I'm saying that, okay, you have F1 or F can be decomposed into Fx, Fy, for example, X, Fy, okay. So that means if I want to draw the triangle, it will be something like this. You have Fx, okay, starting from this point, and then you add up with Fy. The resultant will be F. And if you look at the direction of the arrows, okay, they are not producing a loop. Okay, so you have this green vector is going to the left, then followed by Fy. Okay, that's trying to make a loop, then suddenly stops there. Okay, because F is not following the same direction. Okay, or it's not making a loop. So in this case, we know straight away that resultant is actually not 0. Okay, or basically your summation of force is not 0. However, in this case, we know that summation of force is 0 because the forces are creating a loop whereby it is pushing or pulling the point, okay, to different position, but in the end we'll move it back to its initial position. Okay, so that's the idea. Once we have our triangle, next thing is just to determine the angle within the triangle. So we have 30 degrees as the angle of TCD, so that means here is 60 degrees. Again, here you have 30 degrees. Angle of TBC is 45, so here is 45. Angle here will be 45 as well. Okay, so once we have all these angle, the task now is to determine what's the value of TCD and TBC. Okay, weight is known. This is equals to 25 times 9.1. Right? So we can use, in this case, line rule to solve for TBC and TCD. Let's say I start with TBC first. I know TBC over sine of angle opposing TBC, in this case 60 degrees, will be equals to the weight, 25 times 9.1, over the angle opposing the weight, in this case this angle, 30 plus 45, so we have sine 75 degrees. So TBC is just equals to 25 times 9.1 times sine 60 degrees over sine 75. Okay, will somebody calculate this?
219.9.
219.9 Newton. Is it the same as the answer that we get before? Not the same?
When I calculated using the rectangle method for TBC, right? I get the same as the trigonal method, the trigger one, using the sine rule, right?
Okay. I don't know which is the right answer, but the right answer should be the same for both methods. Okay. So feel free to check back your calculation, right? So the main point here is the step to solve the problem. If the step is correct, you should get the same answer for both methods. Okay. So just for completeness sake, I will show how to calculate TCD using sine rule again. Okay, so we can take TCD over sine of angle opposing TCD, in this case 45 degrees, will be equals to weight again, 25 times 9.1 over sine of angle opposing the weight is equals to 75. So TCD is equals to 25 times 9.1 times sine 55 degrees over sine 75 degrees. So you have your value of TCD. Again, this value should be the same with the values that you have calculated using the rectangular method. Instead of using rectangular component method to solve for TAB and also angle theta, we can also use trigger approach. Okay, again, to use trigger approach, I have to draw this diagram first. Okay, so we start off with the angles that we know. In this case, start off with TBC, 5 degrees. This is our TBC, followed by our weight. In order for the polygon or for the triangle to be a closed polygon, so our TAB should be pointing towards this direction. This is our TAB. And this will be the angle for the TAB, theta. Alright, once we have figured this out, next step is to determine the angle within triangle. Here we have 45. Here we have 90 degrees. Here we have 90 degrees minus theta. As for this angle, it is equals to theta minus 45 degrees. And we know the value of TBC. TBC is known. Okay, weight is also known. It's just a matter of finding TAB and the angle theta. So in that sense, we can use cosine rule. First find TAB. So we will have TAB squared equals to TBC squared plus weight squared minus 2 times TBC times weight cos the angle opposing TAB, in this case 45 plus 90 degrees is equals to 135 degrees. Okay, so you can substitute for value of TBC. TBC is known, weight is known. Okay, this is known values, so we can get the value of TAB in Newton. Right, once we have TAB, we can calculate for the value of theta. Right, for the value of theta, we can use sine rule for that. So in theta, let's say I'm looking at this guy here. So I will have sine theta minus 45 over the side that's opposing this angle, which is W, 10 times 9.1 will be equals to sine. In this case, I'm choosing another side. I can choose this angle, okay, with this side, which also contain theta. Or instead of doing that, I will choose another angle that is known. In this case, 45 plus 90 degrees give us 135 degrees over the line opposing it, in this case TAB. Okay, bear in mind we have calculated TAB before, so TAB is known value, so that means we can simply calculate theta equals to 9 minus 1, 10 times 9.1 times sine 135 degrees over TAB plus 55 degrees. To solve this, you have your theta in degrees. So that's the idea. Which method to use depends on you. Okay, which one you are more comfortable with. Either way, both will give you the same answer. Any question?
In the FBD for B, why is TBC downwards, sir?
Why TBC is downward? Okay. While for free body diagram for point C, TBC is upward, right?
Yeah.
Okay. So it depends on where we look. Okay. So in this case, we are looking at point B, right? Point B. So point B. Okay. And we know that cable can only be in tension. Or basically, we can only pull any point. Okay. So if we are at point B, cable AB must be pulling. Or basically, the direction of force must be upward from point B like this. As for TBC, again, the direction of force must be upward from point B because cable can only pull. So TBC is along this direction. Okay, with the same angle but in the opposite direction. Okay, this is theta. And you have your weight. However, if we are looking at point C, okay, at point C, we have DCD. Okay, again, cable must be pulling point C. So we have DCD at an angle of 30 degrees here. And then we have weight. And this is different weight. Okay, compared to this is another weight, 25 times 9.1. And here we have TBC that is also pulling point C. And when we say it's pulling, it must be outward from the point. Make sense?
Yes, sir. Got it.
Okay. In fact, if you want to visualize it in another way, since we are saying that the system is in equilibrium, right? If we look at the cable BC alone, right? So you have this part is going downward, right? So you have from this figure diagram, you have TBC downward. Okay. Here you have TBC upward, right? And since both of these forces have the same magnitude along the same line of action, but in opposite direction, the sum of them is 0. Okay, sum of the forces is 0. So that means this point here will be in equilibrium. Make sense? This is now
Yes, sir.
another way to check whether your free body diagram is correct or not, especially between adjacent points.